Assalamu alaikum everyone. Today I will be presenting on the topic of nickel ferrite nanoparticle based piezoelectric sensors, their chemistry and their applications in medical devices. This is a comprehensive review of how these sensors are developed, their unique properties and their promising applications in the medical field. This work is part of my submission to Dr. Hamad Majid in the Department of Chemistry. Let's dive into the topic and explore these fascinating developments. Introduction. In the field of sensor technology, piezoelectric sensors have become invaluable due to their ability to convert mechanical forces into electrical signals. These sensors find applications in various domains, notably in medical devices. Nickel ferrite nanoparticles are emerging as a crucial material in enhancing the performance of these sensors due to their unique properties such as high sensitivity and biocompatibility. Today, we will explore how these nanoparticles contribute to advancements in medical technology. What are piezoelectric sensors? To begin with, let's understand what piezoelectric sensors are. These devices operate on the principle of the piezoelectric effect, where certain materials generate an electric charge in response to mechanical stress. This makes them perfect for detecting physical changes like pressure, vibrations, or temperature. Their applications span across various industries, but today our focus will be on their use in medical devices. Nickel ferrite nanoparticles are a type of spinel ferrites basically with remarkable magnetic properties. These nanoparticles stand out due to their high sensitivity, stability, and excellent magnetic characteristics. Their application in medical devices is pivotal, especially in areas like magnetic resonance imaging, drug delivery systems, and energy storage. Their ability to be synthesized in various forms and sizes makes them incredibly versatile for medical applications. Now let's look at how these nanoparticles are synthesized. There are several methods, each with its own advantage. Co-precipitation method. This is a straightforward method involving the mixing of nickel and ferric salts with a precipitating agent like sodium hydroxide. Sol gel method offers control over particle size and shape by forming a gel that is later calcined. Hydrothermal synthesis involves high temperature and pressure, ensuring the crystalline structure of the nanoparticles. Chemical vapor deposition, a more sophisticated method that allows for precise control over the nanoparticle characteristics. These methods allow for the tailored production of nanoparticles suitable for specific medical applications. The next critical step is functionalizing these nanoparticles to enhance their properties. Functionalization involves coating the nanoparticles with polymers, organic molecules, or other compounds to improve their biocompatibility, stability, and functionality. This step is crucial for applications in high-frequency devices, magnetic data storage, and especially for ensuring safe and effective use in medical settings. Mechanism of piezoelectricity. Understanding the mechanism behind piezoelectricity in these nanoparticles is essential. One key process is Magnetostriction, where the material undergoes a mechanical strain in response to a magnetic field. This property is exploited in piezoelectric sensors, where the nanoscale structure of nickel ferrite enhances their efficiency and response to mechanical and electric applications in medical devices. Nickel ferrite nanoparticles have numerous applications in medical devices, tissue engineering. They help in scaffolds for regenerative medicine, aiding cell growth and differentiation. Biosensors used to detect vital signs and biochemical signals. Implantable devices essential for tracking stress and pressure in implants like pacemakers. Energy harvesting. They can power devices by converting biomechanical movements into electricity. These applications showcase the potential for transforming healthcare technologies, making them more efficient and patient friendly. Applications in wearable electronics. In wearable electronics, flexibility and durability are paramount. Piezoelectric materials like nickel ferrite are incorporated into flexible devices for energy harvesting, health monitoring, and smart fabrics. Hybrid printing techniques, which combine screen inkjet and 3D printing, allow for the production of intricate high-performance sensors that are both scalable and customizable. Applications in other fields. Beyond medical devices, nickel ferrite-based piezoelectric sensors have significant roles in aerospace and defense, industrial applications, automotive applications, and structural health monitoring. In aerospace and defense, sensors detect stress and strain in aircraft components. Industrially, they are used in automation systems for feedback and energy harvesting. And in automotive industry, they improve vehicle safety features like airbags and performance monitoring. Structural health monitoring. Ensure real-time monitoring of infrastructure integrity, enhancing safety and maintenance efficiency. Despite their advantages, there are challenges: material risk, performance issues, environmental factors, and cost. Material risks or some materials, PZT contains lead, which possess health risk. In performance issues, sensors may struggle with low frequency signals and brittleness. Environmental factors like temperature and moisture can impact sensor performance. High-quality piezoelectric materials can be expensive, affecting overall cost effectiveness. Addressing these challenges is crucial for broader adoption in various industries. Recent researches. Recent research focuses on enhancing the properties of piezoelectric materials. Studies have shown that incorporating cellulose, nanocrystals, and nickel ferrite into composites increases the piezoelectric performance. These advancements are paving the way for more efficient sensors and energy harvesting devices. Future perspectives. Looking ahead, the integration of nickel ferrite nanoparticles into piezoelectric materials offers exciting possibilities like energy harvesting, sensors that power themselves through mechanical vibrations, and in variables, structural health monitoring, flexible sensors for real-time monitoring, and biocompatibility. Further research could lead to implants and biological monitoring sensors, enhancing patient care and medical outcomes. Research directions. Future research aims to refine the synthesis and functionalization of nickel ferrite nanoparticles. Techniques like electron spinning and solution combustion synthesis are being explored to produce homogeneous, high-performance materials. This will be key in developing more effective and reliable piezoelectric sensors. Lastly, conclusion. In conclusion, nickel ferrite-based nanoparticles piezoelectric sensors offer significant benefits for medical devices and other applications. They provide a blend of sensitivity, stability, and biocompatibility, making them ideal for the next generation of healthcare technologies. Ongoing research and interdisciplinary collaboration will be essential in overcoming current challenges and working and unlocking their full potential. Thank you.